All right, so this is acidic or basic salts. So we're just looking at different salts that we can put in water that might make the pH of the water change. Okay, so acid-base properties of salts. So if I put NaCl in water, I make sodium ions. And it could make sodium hydroxide because the positive ion would be attracted to the negative hydroxide ion. But since NaOH is strong, it completely dissociates and it doesn't stay together. All right, and the same thing happens with chloride. If I put that in water, it could make HCl, but since HCl is strong, it doesn't, so it completely dissociates. And so that means that this salt overall is neutral because both this makes a strong base, this makes a strong acid, they both dissociate completely, and so that makes this neutral. All right, and then for aluminum chloride, okay, aluminum in water could make aluminum hydroxide. Now that's weak, right? So it makes a weak base and it stays together in solution. So weak base. Now Cl does not. It dissociates completely, and so this is going to be a strong acid. All right, and so since this produces this excess hydrogen here, when it takes the hydroxide out of the solution, so this hydroxide is no longer part of the water anymore, and then this didn't take anything out because it completely dissociated back to hydrogen and chloride, that means that this is going to be acidic. All right, so the easy way to do this is label, okay, this makes a weak base, this makes a strong acid, so therefore it's going to be acidic because strong overpowers weak. But really it's because of the formation of the weak base, pulling out the hydroxide ions and leaving excess hydrogen ions that makes it acidic. All right, so let's look at lithium fluoride. Lithium fluoride, lithium again could pull out hydroxide, but since it's strong, it dissociates completely, so it doesn't pull anything out of the water. And then fluoride in water could pull out the HF, and since HF is weak, it does do that, and it makes HF. We have an excess of hydroxide in the water because it pulled out. So if we have H plus and OH from water, and we start pulling out the hydrogens, then that means that this is going to increase the pH. All right, so this is basic. And when you have a weak base, so this is weak base, and a weak acid, then that means that you're going to have to compare Kas and Kbs and figure out which one is going to produce acidic or basic salt. But I haven't seen that on the AP test in so long, I'm not even going to talk about it. Let's try a couple of these. So will the pH of the solution be acidic, basic, or neutral? Okay, so for the first one, KBrO2, this produces potassium hydroxide, which is a strong base, and this produces bromous acid, and so that's going to be a weak acid. And so since we have a strong base and a weak acid, it's going to be basic. Okay, and then we can look at B, which is going to be calcium bromide. Okay, so calcium is going to make a strong base, and hydrobromic acid is a strong acid. So since it's a strong base and strong acid, this makes a neutral solution. All right, and then we have silver nitrate. So this is a weak base, and this is a strong acid. And so this makes an acidic solution. All right, and then number 2 says for each of the salts above that are acidic or basic, write the reaction that will occur in water that causes the pH to stray from 7. All right, so if we look at the only ones we have to do is this one and this one, because it says the only ones that are acidic and basic. All right, so KBr2, the part that we need to look at is this part right here, because it's the weak part, right? Strong, we use it to determine if it's acidic or basic, but it's not really what's making the pH stray. What I have is BrO2 negative, and it's going in water. And so it's going, since it's negatively charged, it's going to pick up a hydrogen. And it's going to leave a hydroxide because it stole a hydrogen. So that's the reaction for that first one. And that's why it's basic, because it's making hydroxide. And that's what we determined it was going to be. Okay, in the next one we have silver nitrate. So looking at this, I don't care too much about what's strong. What I really want to look at is what is weak. So I have silver ions, and this is going to go into water. And so since water is hydrogen and hydroxide, and this is positive, it's going to pull out the hydroxide because hydroxide is negative. So I'm going to get silver hydroxide plus hydrogen. And so since we're making hydrogen here, and since this is going to go up, this is what makes it acidic. And so it makes the pH lower than 7. And this makes the pH greater than 7. All right, so here's a relationship between Ka and Kb that we haven't talked about yet. And because we're dealing with salts, this has to do directly with them, usually. So this Kw is equal to the Ka times the Kb for conjugate acid-base pairs. All right, so if I have acetic acid has the Ka of 1.8 times 10 to the negative fifth. So if we need to know the Kb for, let's say, acetate, then we could just use this equation and plug our values in. So I'm going to divide both sides by 1.8 times 10 to the negative fifth, and I find that my Kb is equal to 5.6 times 10 to the negative 10th. And so that would be the Kb for this. All right, so let's look at some examples where we use this. All right, it says calculate the pH of a 0.3 molar sodium fluoride solution. So, and then I'm given a Ka for HF. So sodium fluoride is a strong electrolyte, and we have 0.3 molar sodium fluoride solution. So this completely dissociates 100%, and we get 0.30 molar sodium ions and 0.30 molar fluoride ions, right? And so this goes away because it splits apart completely. Now, if sodium was to interact with water, it would interact with the hydroxide. Sodium ion was to interact with water, it would interact with hydroxide. And this is a strong base, and so it would just stay completely dissociated, right? Well, if fluoride interacts with water, it's going to interact with H+. So my reaction would be this, because HF is a weak acid. So those two get stuck together, right? And I have to have for this, because I've got this guy, means that that's a base. So if it's a base, it has to have a Kb. And right now, all we have is this Ka. So before I do anything, I have to find out what my Kb is. And so Kb for F negative is going to be equal to the 1 times 10 to the negative 14 divided by the Ka for the acid. And I get that it is going to be 1.39 times 10 to the negative 11, or 1.4. So that's the Kb for fluoride, because that's the conjugate base of HF. All right, so now I can set up my rice table, and I know that I'm starting out initially with 0.3 of this, none of the acid and none of the hydroxide. This is going away, and this is going up. So then I'll have x squared over 0.3 minus x is equal to 1.4 times 10 to the negative 11. And this x becomes negligible, so I have 0.3 times 1.4 times 10 to the negative 11, and that's going to be 4.2 times 10 to the negative 11, and then I'm going to take the square root of that. And x is 2.05 times 10 to the negative 6. That is the hydroxide concentration. So then if I take the negative log of that, that'll give me the pOH. And then subtract from 14, I get 8.31. So it's not very basic, but it's a salt that makes a basic solution in water. It's slightly above 7. Okay, so my next one, this is a salt, right? It's going to be ammonium chloride, and ammonium things are always soluble. So I have NH4Cl, and I have 0.5 molar concentration of that, and it dissociates completely. So I get 0.5 molar NH4, and I also have 0.5 molar chloride. Now, if chloride were to interact with water, it would make HCl, which completely dissociates back into H and Cl. So this doesn't do anything. All right, now if NH4 interacts with water, we have a different story because NH4 behaves like an acid because it's a nitrogen compound with an extra hydrogen. This is a conjugate acid. So it's going to produce H plus in water. All right, so if we look at that reaction, the NH4 is going to donate an H to water. So we're going to get NH3 plus hydronium. So since this produces acid, we have to have a Ka, not a Kb, and we have a Kb right here. So I'm going to take 1 times 10 to the negative 14 and divide by that, and my Ka is 5.6 times 10 to the negative 10th. All right, so I can go ahead and set up my rice table now. This is 0.5. Water doesn't matter. 0, 0, x, x, 0.5 minus x. So I have x squared divided by 0.5 minus x, and that's going to be equal to 5.6 times 10 to the negative 10th. Get rid of this x, multiply both sides and take the square root, and I get that the x is 1.7 times 10 to the negative 5th. So if I take the negative log of that, I get that my pH is equal to 4.78. So I feel like the hardest part of this whole section is knowing whether or not you have an acid or base. And guys, I'm going to show you how I did it when I was a freshman learning this stuff in college. I just knew that if this was a salt, then it was giving me the opposite of what I needed. So this was going to end up being produced instead of being a reactant. So I just kind of flipped it in my head. Whichever way you want to do it, it makes a lot of sense. It's just sometimes hard with all the other stuff that you have going on to remember which one is happening. But if you're given this and there's no HF in it, then you know it's a salt, and you know the F is going to be the reacting species. Here we have NH3 given to us. It's a Kb, so this must be acting like an acid, and I have to find my Ka. But that's just, I don't know, that's what I always did.